Okay, in this problem, we need to evaluate this limit and give a graphical interpretation for that limit. Okay, so let's go ahead and write that down. The limit as x approaches 3 of x squared minus 6x plus 9, all of that over x minus 3. Okay, now our first inclination, perhaps, is to try to appeal to continuity. If this function right here represented a continuous function at this x value, then evaluating the limit is easy. I just plug this x value in. But I can't do that here. This is not continuous at x equals 3, and I know that because 3 is not even in the domain of this expression. If I were to plug 3 in, notice I get a 3 minus 3 on the bottom. That's 0. You are dividing by 0. That's a no-no. So 3 is not included in the domain. If we call this f of x, f of 3 does not exist, and consequently this thing can't be continuous at 3. So that's out. Okay? So what can we do? Well, let's play around with this a little bit. One thing you might notice is this top might look familiar here. It's got a nice perfect binomial square form, doesn't it? In other words, we can factor it. And in fact, it factors into x minus 3 quantity squared. And of course, it's still sitting over at x minus 3. All right? Now, of course, those of you proficient at algebra will immediately want to cancel one of these common factors, a common factor of x minus 3. Okay? And you would be right in doing so. If we were to go ahead and let's say cancel that guy off with that denominator, leaving us with the limit as x approaches 3 of simply x minus 3, we'd be correct. But make sure you understand why. This is a function where we cannot plug 3 in. 3 is not in the domain of this function. This is a function where we can plug 3 in and get something out. Granted, we get 0 out, but that is a real output. This function and this function are different. Now, as it turns out, these two will agree in output for every value of x except for x equals 3. And since the value of the limit doesn't depend at all on what this function does at this value, at 3, then this limit and this limit should be the same. Okay? So now we start anew with this limit. Here again, our first inclination, and I'm going to put parentheses right here and here just for clarity, our first inclination might be to try to appeal to continuity. Are we looking at a continuous function here? If we are, then I can just plug 3 in and out pops the value of my limit. Okay, because in a continuous function, remember, the value of the function and the value of the limit agree in value. Is this continuous? Well, sure. Y equals x minus 3 is a linear function. It's a polynomial function, and we know polynomial functions are continuous everywhere, in particular at x equals 3. So that means I can just plug 3 in and get 3 minus 3 or 0. Okay? So that's the value of this limit, which also agrees with the value of this limit. And I've answered half my question. Okay? Now, as for our graphical interpretation, look, we know what the graph of this looks like. That's just a linear function. That's the graph of y equals x minus 3, slope 1, y-intercept of negative 3, something like this. Okay? Working backwards, remember, this agreed with this in all outputs except for what happens at x equals 3. At x equals 3, we just had a problem. We couldn't evaluate it. It was outside the domain. So at x equals 3, which would be right here, we have a domain issue. We have a hole. We just pluck that point off of the graph of this line, and that's the effect of throwing back in this multiplication by an x minus 3 over an x minus 3. Okay? So, what's the graphical interpretation? It's a hole. In particular, it's a hole at this x coordinate and this y coordinate. That's our graphical interpretation. Now, did we have to graph this thing to come up with this graphical interpretation? Absolutely not. We know that the limit exists because we were able to find it. Okay? So that gives us basically two options. We have something like this. Okay, maybe it goes down, maybe it forms a U, maybe it's an upside down U, it doesn't really matter. But the limit tells us this much of the function exists. And then we've got to figure out what is the function itself doing. Okay, what is this guy doing at 3? Well, we know we can't plug it in, so it's not doing anything. There's no points on this line. Okay, that tells us we have a hole. And more generally, one of three things has to happen. Okay, if you know that you have a limit, you have at least this much, then when you evaluate the function, it's either going to land outside of where you think it should go, it won't be there at all, or it might land right inside the hole. Okay, filling it and thus making it not a hole. All right, so the two cases that lead to holes are when you have a limit existing and then at that particular C value you're either outside of your domain like we are here, or when you plug it in you get something that disagrees with the value of the limit. Okay? All right, so long story short, algebraically, what do we mean here? We got a value for the limit, and then we check if this right here is f of x, what is f at this value? What is f at 3? Well, in this case, it's undefined. And so the fact that you have a limit, but f of 3 is undefined makes it a hole. If you had a limit and f of 3 was anything but this value, you have a hole. If you have a limit and f of 3 was this value, then you would have a point of continuity. Okay, so we never actually have to graph this thing. All right, so that's the value. That's the graphical interpretation. We're all done.